So we're doing beta oxidation now. And so ultimately, remember, beta oxidation is a metabolic breakdown of these free fatty acids. And you're going to be breaking it down to make acetyl-CoA. And that's the important thing here. And so we're going to review just a little bit over what we had covered before the last time. So it breaks it down 2 carbons at a time. Most of your free fatty acids are even numbered. There are some that are odd numbered, and so you have to do something a little different. Okay, but we'll go through all those special cases later on. So normally we break it down 2 carbons at a time. So, and that was important because where does the acetyl-CoA go from there? First of all, when do you break down your fatty acids? When you need energy. And so where will the acetyl-CoA go? To the citric acid cycle, ultimately, okay? And then we also talked briefly about why it was called beta oxidation. What does the beta indicate? Like what carbon gets oxidized. Okay. Which, if this is the ground zero carbon, here, let me change they always put the default as, if this is ground, so here's your ground zero carbon. Where is beta? 2. So that would be C alpha. This would be C beta. And so it's going to be the one that's going to be getting oxidized in the process of beta oxidation. Okay. I don't know if we actually started any of the steps yet or not, but there are only 4 steps of beta oxidation. I call it a spiral because you start large, you end up knocking off 2 carbons through those 4 steps, you go through it again, knock off those 2 carbons through 4 steps, and so on and so forth. So ultimately we get down to acetyl-CoA. So everything comes to acetyl-CoA. All right, so let me hit, here we go. So one thing in general, whoops, didn't mean to do it that way, is they like to use this term acyl-CoA. Remember, acyl is referring to this, and that way we can say that this R can be small or it can be really, really large. For example, arachidonic acid has 20 carbons total, so it's really big. And so that's why they call it acyl-CoA, whereas acetyl-CoA has how many carbons in it? 2. Right? It's just this and a methyl group. And then, of course, this is coenzyme A, and this is the important thioester. So if we notice here, we're going to go from acyl-CoA to what's called a trans-enoyl-CoA. It utilizes an FAD. FAD becomes FADH2. All right. One thing, remember my cheat sheet way from organic chemistry? How can we tell when a carbon got oxidized or reduced? What happens when a carbon gets oxidized? You can increase the number of carbon to oxygen bonds. What was another way for us to tell if it got reduced? Besides decreasing the number of carbon to oxygen bonds, it was also increasing the carbon to hydrogen bond. Well, if you notice here, we're getting oxidized. You could go through and figure out all the steps and everything, figure out all the oxidation numbers, but we're reducing the number of carbon hydrogens. So there's a carbon to hydrogen, there are 2 here, and now there's only 1. So this is just another way of, a cheat sheet way of doing the fact that it got oxidized. And it's carbon number 2 that's being oxidized here. So, all right, so I always said that there's that little caveat that trans fats are not naturally occurring, with 2 exceptions. And this is one of the 2 exceptions because briefly it's trans fat. However, what's really important to note here is it never leaves. So that's why they always say that trans fats are not naturally occurring, because we don't naturally get that from, our body doesn't make trans fats and release it. It stays during beta oxidation. Okay, and I'll explain how that happens in a moment. So it's never a transient process. So that's why you don't have to worry, assuming that you're healthy, that your body during this process will create the trans fat and it escapes and it causes, plaque buildup and atherosclerosis. Where's the one place that we get trans fats non-naturally? Like, why do we have to worry about it? Where did the trans fats come from that are bad for us? From your food, okay. All right. So what class or classes of enzymes can this be? This is always a good review for enzymes. It's a dehydrogenase. Okay, and we know it's a dehydrogenase. Why? FAD to FADH2. It is in redox. Okay, and then if we were going to name this one, what could we name it? What's being oxidized or reduced? Right. And so this literally is acyl-CoA dehydrogenase. Don't say acetyl-CoA dehydrogenase because that means it could only do 2 carbons. This one means it's more promiscuous. It can accept things that have larger larger fatty acids chains. So yep, this is acyl-CoA dehydrogenase. See, not hard. Once we know the enzyme names, that's like half the battle, if not more. So for the second step, we have a hydration reaction. So we take that trans fat, so to speak. Once again, it's not leaving the enzyme complex. And we're adding a water, so we're hydrating it, to make this beta-hydroxyacyl-CoA. And I know it sounds really scary, but if you break it down, it should make sense. The CoA, the acyl, so that's the ground zero carbon, so that's C alpha, C beta, and it has a hydroxy group. Technically it's L because it's it's inside the enzyme, so that's why it's stereospecific. But the important thing here is it's beta-hydroxyacyl-CoA. So what class or classes of enzymes can do hydration reactions? It's not a hydrolase, but you're really close. Hydratase. Okay? And if we were going to, what's being hydratase? If we're going to name it, could we name this one? Yep, this is, that's supposed to say enoyl-CoA hydratase. If you said trans-enoyl-CoA hydratase, that's also correct. Okay, that's fine. Oh. So the name here tells you exactly what it's doing. It's adding water to the enoyl-CoA. When you do, and it may be kind of hard to tell where that water is. There's the OH for the water, and there's one of the hydrogens. Because before we just had one hydrogen here, and now we have 2. So we are adding a water across that double bond. It's just that the C beta gets the hydroxy group, and the C alpha gets a hydrogen. And in doing so, we're activating it for the next round. Okay, so now we're at step 3. Remember, there are only 4, so we're almost done. So once again, I just want to point out that it's a generic acyl-CoA, because the biggest mistake that I see people make, and even in the books I've seen them do it before, is they, instead of saying acyl, they'll say acetyl, which that's only true at the very end, right? Whenever you get down to 2 carbons. And so it's beta-hydroxyacyl-CoA. We have an NAD plus becoming NADH. And in the meantime, so is this alcohol being oxidized or reduced? It's being oxidized. I mean, that tells you right there. But it's being oxidized. So we have 1 carbon-oxygen bond, and now we have 2. Okay, so therefore, by default, that means the NAD is being reduced to NADH. I forgot to point it out before, but the FADH2, that was so important. Does anyone know, where does it go? It goes to another metabolic pathway. It's going to make 1.5 ATPs in the electron transport chain. Okay, that's where it goes. Just like this can go on and can make up to 2.5 ATPs in the electron transport chain as well. Okay, for the ETC/oxidative phosphorylation pathway, because they are symbiotic with respect to each other for healthy people. Right. So what class or classes of enzymes can this be? This is a dehydrogenase as well. Whoops, my handwriting is even worse than normal today. That's dehydrogenase. So if we're going to name this one, what can we name it? This is beta hydroxy acyl CoA dehydrogenase. I did a little bit better job with that word. There, that way you can see the pretty typing. So we had step 1 was oxidation, step 2 was hydration, step 3 was oxidation, step 4 is cleavage. Oh, whoops, I forgot to show you. Step 4 is cleavage. Let's jump the gun there. You're going to get two products, one of which is acetyl-CoA, which can go on, to the citric acid cycle. Or there are other reasons why you use acetyl-CoA, but usually when we're talking about this, we're talking about times that we're energy deficient, so we're going to go on. The other product, with the exception being the very, very last round, the other product is going to be another acyl-CoA, but it's going to have 2 less carbons. So if we start off with 16 carbons, now the other product will only have 14. This is using terminology from organic chemistry. Okay, the Claisen reaction, and we have a reverse Claisen reaction, and so on and so forth. Which, if you remember, it has to do with the fact that this hydrogen can leave really easily to make this an enolate, to where it can then go and attack, or look like it's attacking. Okay, and we'll see it in a moment, how it works. All right, so we have, oh, and I forgot to point this out, this is called beta-keto acyl-CoA, which should make sense once again, because we have ground 0, C alpha, C beta, is a ketone group, and so that's why it's called beta-keto acyl-CoA. This is the most difficult step because it has a special name. Okay, what are some of the functional groups that are involved? I already said ketone. What's another functional group that's around here? We have ketones, thioester, and we have one other one. This one, what's this one called? Thiol. And this is the one that the enzyme is named after. This is thiolase. Which you're probably going to forget it, but thiolase is actually involved into 2 metabolic pathways. Yep. So it's thiolase. All right, so once again, there were 4 steps. There's oxidation, then hydration, oxidation, then cleavage. And that one video I was talking about uses a Ting Ting song that goes through that. It's stuck in your head. Okay, so this is overall what's going to happen. Now, I've seen people overthink this sometimes. So it's the spiral. It goes over and over and over again. So for example, if we have something that has 18, see there's 18 carbons. There's 16, 17, 18. It does not go through 9 rounds. It only goes through 8 rounds because that last round you end up with 2 acetyl-CoAs. So sometimes questions have asked, how many rounds does it go through? What you do is you would literally take, 18 divided by 2, which is equal to 9. and then -1, okay? So there's 8 rounds. And that's because that last round you get 2 acetyl-CoAs out of it. So if we had 16, we have 16 divided by 2, which is 8, -1 is 7. It only does 7 rounds. Sometimes people either overthink it or, I don't know, underthink it or something. But the reason why I want to point that out is this is where we get lots and lots and lots of energy. So this one 18 carbon-containing fatty acyl group, it goes through 8 cycles, and it's going to make 8 equivalents of NADH. Each of those can go up to make as many as 2.5 ATPs. It's going to make 8 equivalents of FADH2. Each one of those can go up to make 1.5 ATPs. And so we can see this is where we get a lot of energy, a lot more than you do from just a glucose going through glycolysis in the citric acid cycle. And so that's why 2.5 would be 16, be 20 here, and 1.5 would be 12. So 32 ATPs, up to 32 ATPs. So you can get a lot of energy out of this system. Then I just have a couple of cartoon figures showing the exact same thing. This one I like because it shows you the spiral. So just to review, we have our fatty acyl-CoA. I like the fact that it shows you C-alpha, C-beta. You have your acyl-CoA dehydrogenase to make your enoyl-CoA, trans-enoyl-CoA. That delta 2 just lets you know, remember, if you think way back to last semester when we did fatty acids, that lets you know where the double bond is. The double bond is at carbon number 2. Okay, and so we made a trans-enoyl-CoA, we have enoyl-CoA hydratase. Now we have beta-hydroxy acyl-CoA. We have the beta-hydroxy acyl-CoA dehydrogenase that comes in to make it beta-keto acyl-CoA, and then we have thiolase, which kicks off 1 acetyl-CoA, and you have 2 less carbons, and you just go over and over and over again. Plus, it's got the cute little scissors here. And then this is the same. Whoops, let me make it smaller. This is the same thing. This is from your current book, I think. Well, it's from a previous edition of your current book, but it shows you the spiral this way. I haven't checked to see if that link would still work, but it doesn't work right now since I don't have internet access right here, but we can see the same thing. Are there any questions over the 4 steps? Okay. Take a swig. So we already talked about where the products go and why that's important. Remember, acetyl-CoA itself goes into, if you're needing energy, it's going to go into the citric acid cycle at step 1, okay, to make citrate. Now the FADH2 and the NADH goes to the electron transport chain in the mitochondria, typically. I mean, it can be used for other things, but if you're needing energy, that's what's going to be going. And we cover the electron transport chain soon. I can't remember if that's next chapter or not. Okay, so those were your saturated fats. But what about if it's an unsaturated fatty acid? So first of all, what is an unsaturated fatty acid? What does an unsaturated fatty acid have? Double bond. Okay. And is a traditional cis unsaturated fatty acid, is that a good fat, quote unquote good fat, or is that a bad fat? That's a good fat. Okay. So what happens here is it's going to take a couple of additional reactions because it doesn't fit in there. Right? We looked at something that had all carbons and hydrogens. So the first thing we're going to look at is a mono-unsaturated cis fatty acid. So that means it's going to have one double bond in it. It's cis. All the naturally occurring ones are cis. And this is oleate acid. Okay. And this is the one where when we were doing this kind of thing, remember we'd have like the delta 9 to tell you it's between carbons 9 and 10. So this is one of them. This would be a delta 9. The first few rounds of beta oxidation are just like normal. It's going to be normal until you get that double bond 2 carbons away from that carbonyl. Okay? Then what happens is that hydratase can't act on a cis fatty acid. It only recognizes trans fatty acids. So therefore, we have to actually have something come in to help it out in order to make it from the cis fatty acid to a trans fatty acid. Okay, once again, you don't have to worry about this leaving. Right? So here we go. There are 18 total carbons right here. It undergoes 1, 2, 3 rounds, just like normal. But now the problem is this carbon right here has the cis bond. The beta carbon does. And we need that double bond to be a trans double bond between carbons 2 and 3. And right now it's between carbons 3 and 4. So there's carbon 1, 2, 3, 4. Ground 0, C alpha, C beta, and delta. Okay, and we want it between alpha and beta. All right, so that means we have to have an enzyme come through and take it from a cis formation to a trans space formation. Formation of a trans bond. It is a transformation of itself. What class or classes of enzymes can do this? And if you think about this, what is the relationship of cis to trans? What are they with respect to each other? They are isomers. And so what class of enzymes can do this? Isomerase. This is an isomerase. See? Know your enzyme family names because it helps. Okay. Now we have to name this specific isomerase. And so, so to review so far, remember this oleoil, it's hard for me to say, I'm just going to call it acyl-CoA. This is another type of acyl-CoA. Okay, so what can we call this one? Well, actually, technically, it's not an acyl-CoA, it's an enoyl-CoA. I'm sorry, I misspoke right there. This is an enoyl-CoA. This just tells you the specific, means 14, dodec, okay? But it's an enoyl-CoA. So if you were going to name this one, what would you name it? Because this enzyme's got to be able to take more than one type of fatty acid. So it's not going to be called dodecanoyl-CoA, blah, 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 blah. So what would we call this one? So it's an enoyl-CoA isomerase. Now this one is very, I hate saying specific, but it is in the sense that it's called delta 3. Delta 2 enoyl-CoA isomerase. And what that means, once I explain the name for it, it should make sense. What this tells you is it's going to take it from having a double bond to the 3 position to having the double bond to the 2 position of enoyl-CoA in its isomerase. Once you have that trans fat there, it just goes through normal beta oxidation. Everything is fine and dandy. So here, I'll do it the way it shows it. It's got pretty spelling, not spelling, but pretty handwriting. Delta 3, delta 2, enoyl-CoA isomerase. Because it literally tells you we're going to take it from the delta 3 position to the delta 2 position. Well, from one isomer to the other isomer.
Now, this was basically step 1 if it was a cis instead.
Pardon?
Because in step 1 with beta oxidations, it was just trans enoyl-CoA.
Right, so this would take that place. And so you can imagine before, we would have, normally we have that spiral, spiral. But then we get down there to where it just kind of has to jump through one more step instead of that step 1, and then it goes through the spiral once again. Okay, so what happens if it's a polyunsaturated fatty acid? That's one thing if it was just monounsaturated. Now it's a polyunsaturated fatty acid. So there are lots of, and they're all going to be cis bonds if they're naturally occurring. So we have two problems, or potential problems, let's say. One of them is just what we've seen before. Is it a cis versus? One of them was what we've seen before. Is the location of a double bond. The other one is it a cis versus a trans fat? Like what happens if you have a trans fat in the wrong spot? If you have a trans fat in a normal spot, I should say normal, in the spot that the enzyme, the hydratase, accepts, and it just goes on. But if it's in the wrong spot, then you're going to have to move it. Okay? So here we have to think about, that's supposed to be a beta sign, but it didn't copy over. For beta oxidation, we have to think where the double bond needs to be for that hydratase to work. Remember, that double bond's got to be at position 2, not position 3. With respect to the carbonyl, okay, the ground zero carbon. It can require 2 auxiliary enzymes, and this is just an example. This is linoleic, which we call it linoleic acid, but in reality, remember, it's going to have a CoA on it, so that's why it's called linoleoyl-CoA, and tells you it's at positions 9 and 12. That's from last semester, that kind of nomenclature that we've seen in the past. I'm going to spend a little bit of time on this. Let me make it a little lower where we can see what's going on. Okay. So what happens here is the first 3 rounds is just normal beta oxidation because we haven't even gotten down to where it was before. Now, the problem is we're here, and this is essentially what we've seen in the past. This just gives you the names. See, that means it's a cis at the 3 position and a cis at the delta 6 position. So this is what we saw just the last time around. So this is the problem that we have here. There's the ground zero, and we're wanting to work at the beta, the C beta, but the problem is the fact that it's a cis double bond. Okay, so how do we fix that and convert it from being that cis to that trans? Like what was the enzyme that we just talked about? That isomerase, and that specific name for that isomerase is delta 3, delta 2, enoyl-CoA isomerase. So see, that's just normal. I say normal, just like what we just talked about, so that there's nothing different. So now it can undergo regular oxidation, beta oxidation again, because it's in the correct. Okay. So then we get to this next. If you did all this yourself, what you're going to find out is we get to this position here, where we've got a trans fat at position 2, but right here at position 4, we also have this cis double bond. So this is our problem. We've got to somehow try to fix this. All right. So, the way that we do this is we have an enzyme that comes through. Oops, that's what I want. That's what I want. We have an enzyme. It utilizes an NADPH. Okay? And this NADPH is going to be reducing the fatty acid that we have here. So before we have both a trans and a cis fatty acid here, now we're going to have a trans fatty acid, but it's going to be at position 3. Okay, so that's what this is trying to tell you. Trans position 2, cis at position 4. So what class or classes of enzymes can do this? What are some of the possibilities? So I could see, yeah, people would say dehydrogenase, so that's a possibility. Ouch, oh, that really hurt right there. That's a funny bone, which is not funny. Okay, so one possibility is a dehydrogenase. This one technically is not called a dehydrogenase. What else? What other classes of enzymes do oxidation reduction reactions? We have oxidases. What others do we have? Reductases. And technically oxidative reductases, which is the same thing. This one is a historical artifact in the sense that this is a reductase. So does it make sense now? Yes, it is a dehydrogenase in the sense that it's doing a dehydrogenase reaction, but the name has stuck around as a reductase. So this one is a reductase. But it's very, I mean, its name is very specific in telling you what it does. It's called, here actually, let me just do it because rather than trying to spell it, it's called 2,4-dienoyl-CoA reductase. Because it's letting you know that it works on, this is called a 2,4-dienoyl, because there's carbon 2, 3, 4. Diene, the oil part just means that it's, an acyl group, CoA reductase. And all of this is probably the one that I've always had the most problems with. It's one that I forget. Like, but if you have like a matching or something like that, then it's easy. It's like, it tells you exactly what it does. It does reductation. It's a reductase on 2,4-dienoyl-CoA. So now we have is this a cis or trans? Trans. And do we want a cis or a trans for beta oxidation? We want a trans. Now, is that position 3, where do we want it to be at? Position 2. Okay. So now the question is, what class of enzymes can change this? What are they with respect to each other? They're isomers. And so what class of enzymes do that? It's an isomerase. And so if you're going to name this one, you would name it and so let's just think about what class of compounds are both of these. These are enoyl CoA isomerase. That's it. This one here before was the specific one that told you that it's going to, be at positions delta 2, delta 3. This one is just literally flipping the trans bond from one position to the other position. So it's enoyl CoA isomerase. Okay, which is essentially just normal beta oxidation for us to undergo what we've talked about so far. Nothing new. Okay. Now where it gets fun. Everybody, moment to get cut up. We've handled saturated fats. We've handled unsaturated fats, both cis and trans. We've handled it when it's in the wrong position, but there's one last class of fatty acids that we have not handled. All of these, what's one thing that they all had in common? They all had even numbers, but what happens, which are rare, but you can, there are odd number fatty acids. Plants and some marine organisms have this. Okay. Ruminants, what's a ruminant? I don't know if anyone's had like zoology. Right, they chew it and they throw it up and chew it and throw it up, and so it's like cows, sheep, things like that. Right, so what they do is they actually form propionate. Okay, and so if you think back to organic chemistry, propionate, what would that be? Obviously the 8 means it's, what does the 8 mean? It's negatively charged, but what in particular? Prop means it has 3 carbons, 1, 2, 3, and what will that other carbon will be? What will be on the end of it? Carboxylic acid. Well, actually carboxylate, but that's propionate. If it's propionic acid, it becomes. All right, but they form propionic acid or propionate. And also another thing is many times propionate is used as a mold inhibitor, and so we get it in our diet that way as well. So we do see some propionate, and then we also get it from sometimes from other whatever we consume. Okay, so we have to have ways to combat it. And we consume it either plants or we can consume it from aquatic organisms. So what happens is you undergo normal beta oxidation until you get to that propionyl-CoA. Once you get into 3, it can't undergo normal beta oxidation, right? It should make sense. You have to have 4 carbons, but we ultimately are wanting to make it still CoA. So it's going to require 3 additional reactions. All right. So we've seen some of this before in just different metabolic pathway, or something similar to this, I should say. So we have propionol CoA, okay, which means it just has 3 carbons. We take bicarbonate and ATP and biotin. So the ATP just means it's going to require some energy, because you get the ADP out of it, so it's an in-between step. Does anyone remember, what did biotin do? We've seen biotin before. What's the role of biotin in general? It's a cofactor. Well, it transfers carbonyl groups, okay? Which is essentially what this is doing. See, we're transferring the carbonyl from the what would be the CO2 from bicarbonate to this position right here, okay? So it transfers carbonyl groups. What class of enzymes can do this? What were these enzymes called that can... It could be a transferase. What was this one, with this class in particular? What is it? What specifically? What group is it? I thought you started saying, it's a carboxylase. If you said carboxyl transferase, I'd give it to you, because that's what it's transferring, and people would know what you're talking about. This is carboxylase. And then we have to name it specifically. What carboxylase is it? Say it with some conviction. Yeah, this is propionyl, CoA, which I didn't give myself much room, carboxylase. Here, I'll go ahead and just show this part. There we go, propionyl CoA carboxylase. This makes what's called methylmalonyl CoA, which is a mouthful. And just a little historical, this is a methyl group, obviously. These 3 right here is called malonyl CoA. It's methylmalonyl CoA, but this, what kind of reaction is actually occurring here? We're going from D-methylmalonyl CoA to L-methylmalonyl CoA. It's an isomerase. And so we had those we had isomerases, there were mutases, and there was that third one that did isomerization. It only happens with sugar. Technically, that's why I wanted to point out malonyls with sugar. Does anyone remember what they called the sugars, isomers of sugars in particular? Epimerase, and this one's an epimerase. And so if you're going to name it, this would be methylmalonyl-CoA epimerase. And I know it says of last semester, but in reality we did epimers also this semester as well, since we started at a little different time. Okay, and this last enzyme has a new coenzyme, a new cofactor that's required. It's coenzyme B12. And coenzyme B12 is really cool. What this does is kind of blocked it up, but this is changing places between the acyl-CoA portion and that hydrogen. So in essence, it's moving it down to what will be the end. So what class or classes of enzymes can do this? There are 3 possibilities. It's not really a transferase, so it's not transferring it from one thing to another. So what is the difference between L-methylmalonyl-CoA and succinyl-CoA? Like the only difference between these, when you swap 2 functional groups with respect to each other on the same molecule, they are, what are they with respect to each other? They're isomers. Like literally, they're isomers. Like if you had given them locant numbers, like 1 versus 2, I mean, that's all it is. And so we have 3 possible. One is epimerase, and technically succinyl-CoA is no longer considered sugar, so it's not epimerase, I'll tell you that much. So that leaves you 2 other possibilities. What are the 2 enzyme families that do isomerase reactions? Mutases and isomerases, and this one is a mutase. It's called methylmalonyl-CoA mutase. Pardon? I didn't hear you. It sounds Hawaiian. I can use it now. Sounds awesome. Okay. And so vitamin B12 comes from cobalamin. And I actually think that I want to give more time to it. I have a few slides on it, just because we don't get to talk about it a lot, and it's really cool. But plus, it's important. We only see it a couple times, and you probably won't get to talk about vitamin B12 in any other classes, most likely. And so I think what I'm going to do is I'll go ahead and I'll stop for today.